Our lesson today is on inverses, and you will notice that we have a number of learning targets: finding the inverse of a relation, finding the inverse of a function given an equation, graphing an inverse, and verifying that two equations are inverse functions. So what is an inverse? An inverse switches the x and the y of the relation. Inverses are indicated with an exponent to the -1 power. Okay, so the inverse of f of x is f to the -1 of x, and the inverse of y is y to the -1. All right, I'll be honest, my favorite ones to do are the ones that involve tables or sets. All right, we're going to have x, we're going to have f to the -1 of x, and we are just going to switch these two values. So my y becomes my x, and my x becomes my y. Switch them. Switch them. That's it. As we look at a set, draw your braces, start your ordered pair, switch your x and your y, comma, switch the next ordered pair, comma, switch the third ordered pair, and finish off your set. Okay. I'd like you to pause the recording for a minute and try the next two on your own. And check your work, please. Alrighty, so what do we do when we have an equation? Well, we're still going to switch that x and y, right? But after you switch the x and y, you have to solve for y. So we start off by switching. X equals -2y plus 5. And now I need to get y all by itself. I'm going to subtract the 5 from both sides. And then I'm going to divide both sides by -2. I'm not quite done here. First off, the y needs to come first. Secondly, I can put this in slope-intercept form, clean it up a little bit. So -1/2 x, a negative over a negative will be a positive, 5/2. I started with slope-intercept form of the line. Y equals mx plus b. Slope-intercept form. You're supposed to remember that from Algebra 1 and from geometry. I'm going to turn on a light here on my desk and see if we can get rid of the shadow a little bit. All right, let's try the next one. Switch your x and your y. X equals 1/3 y plus 6. Now let's isolate the y, subtract 6. Let's isolate y by multiplying both sides by 3. When you do that, put parentheses around your x minus 6, because when you multiply both sides by 3, you have to multiply the x by 3 and the -6 by 3. Okay, not quite done. Can't have y at the end. Y has to come first. And I should go ahead and distribute this. So 3x minus 18. Now for our next one, we're using f of x instead of y. Go ahead and start off by making it a y. Y equals 7x plus 18, and then switch your x and y. Let's isolate our y. Subtract 18 from both sides. Divide by 7. And clean it up. Y equals 1/7 x minus 18/7. Glad I'm not actually graphing that. 18/7 would not be any fun. Number 8. Y equals 1/2 x squared. Switch your x and y. So x equals 1/2 y squared. We need to isolate y. So we're going to multiply both sides by 2. All right, ladies and gentlemen, what do we do to undo squaring y? What's the opposite of raising a number to the second power? And the inverse operation would be the square root, right? Squared and square root are inverse operations. In other words, they undo each other. So I want to take the square root of both sides to get rid of this y squared. And y is going to equal the square root of 2x. That's from Algebra 1. And you should have seen it in geometry when you had to take the square root of a number to the second power. Okay, so what do we do when we have a graph? Choose at least one point from each quadrant the graph is in. Now that really applies to problems like number 2, where you've got a continuous function. I would choose my intercepts, 1 point from quadrant 1, 1 point from quadrant 3. In number 1, where you just have distinct points, you have to do them all. Number 2, create a table of values. Then switch your x and y values and graph your inverse. Make sure it has the same shape as the original. All right, if you start off graphing a parabola and you end up with a straight line, you messed up somewhere, right? If it's a U shape, it's got to come out like a U shape in the end. So our first example has separate points, distinct points. So I'm going to have to do every ordered pair here. -1, 2, 3, 4, -5, 0, and -2, -3, 0, 4, and 2, 2. So I am going to switch that x and that y. 0, -5, -3, -2, 4, 0, and 2, 2. I'm going to graph it. 0, -5. -3, -2, 4, 0, and 2, 2 is actually in the same place. Okay, this is interesting. This is very interesting. And you know what? I'm going to highlight these points because as I'm looking at the screen, I'm seeing it's kind of hard to see. So I'm making them pretty big and I'm highlighting. And here's the interesting thing I want you to notice. There's some symmetry here. And that symmetry is on the line y equals x. It's a reflection from geometry, right? This point moved to here. It was half a block away, so we went half a block above. This point was 1, 2.5 diagonals, half, 1, 2 diagonals. This point was on the line of reflection, so it stayed put. This point was 2 diagonals above. We went 2 diagonals below. All inverses do this. They are reflections across the line y equals x. Let's look at number 2. All right, I need a table. I always start with my intercepts. So I'm going to start with these 2 points. I've got 0, -1 for a y-intercept and 3, 0 for an x-intercept. Then I need a point here in the first quadrant. This one will work, right? Because I have a slope of 1/3. So this is 6, 1. And I need a point here in the third quadrant, -3, -2. Then I'm going to create my new chart. -1, 0, 0, 3, 1, 6, -2, -3. Let's see if I graph this in a different color. -1, 0. Yeah, that shows up better. 0, 3, 1, 6, -2, -3. Going to use my straight edge. And let's take a look and see if it's symmetrical like our last one was. Y equals x. This point, 1, 2.5 diagonals away, 1, 2.5, symmetrical, 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 symmetrical. It's a reflection from geometry. All right, I want you to pause the video and try numbers 3, 4, and 5 with your partner, and we will come back in just a moment. All right, so I am starting number 3 with my x and y intercepts. I have -4, 0, 0, 0, and -2, -4. Okay, I need one more pretty point here in the third quadrant. I'm going to take this one, -3, -3. I need one in the first quadrant. Let's see. There's one. 1, 4. And in the second quadrant, I can pick up this one, -5, 4. So we're going to switch these. And we're going to graph them. 0, -4, 0, 0, 4, -2, -3, -3. That point stays the same. 4, 1, and 4, -5. All right, so I have a parabola that looks like this. Is this inverse a function? No. The inverse is not a function. Right? My inverse does not pass the vertical line test. Right there, I'm going through 2 dots on a vertical line. Now, we knew that was going to be the case just by looking at the original function, right? We've been asking you if functions are one-to-one. We've been asking you to use that horizontal line test. This function is not one-to-one. That means the inverse is not a function. This is going to be important later this year. Let's take a look at number 4. X and Y. Start with your intercepts. Ooh, I don't like that one. I'm not going to do that one because that's not a whole number. I want pretty points. So 0, 3, and 1, 2, 3, 4. -4, 0. I like this point. -3, -3. And that gets me my point in the third quadrant. I also need a point in the first quadrant. This one's going to work. 3, 3. Switch them. Okay, 3, 0. And 0, -4. Right? -3, 3 is not going to move. And 3, 3 is not going to move. Connect them so you get the same shape. Okay, is this inverse a function? No. So this is not a function. Right here, not passing the vertical line test. But it also didn't pass the horizontal line test, right? Right here. And right here where it's constant, this was not one-to-one. So we knew that up front. Let's try this one. All right. 0, 0 makes a lovely point. Here's a pretty point. -1, 1. Ew, ew. That one's decent. -2, 4. I'm only in that one quadrant, the second quadrant. So x, y to the -1, switch them. Let's see, 0, 0 will stay the same. 1, -1, 1, 2, 3, 4, -2. And this has to be a curve. Didn't quite hit my point, but you do the best you can. This time the inverse is a function. These are both functions. That's important. All right, so how can we verify if we have two equations as to whether or not our inverses, the two equations are inverses of each other? Okay, so are these functions inverses, or verify these functions are inverses? And it's going to take us back to a concept we did when we did compositions of functions. We're going to do f of g of x, and that has to equal x. And then we're going to do g of f of x, and that has to equal x. You have to check both. Unless the first one doesn't work, then you're off the hook. So let's start with the first one. F of g of x. So for my x value, for f, I'm going to substitute g, 2x minus 5. Keep the plus 5 and divide all of that by 2. So let's simplify this. 2x, negative 5 plus 5 is 0. Still have to divide by 2. And 2 divided by 2 equals x. So far, so good. Now let's try the other composition. G of f of x. Start off with g. So 2 times, and replace x with f of x. X plus 5 divided by 2. Don't forget to write down all of g. That minus 5 is important. Okay. The 2 and divided by 2 cancel. So I have x plus 5 minus 5. 5 minus 5 is 0. So this is just x. Yes. Both compositions equaled x. Let's try the next one. F of g of x. So 3, replacing x with all of this. 1/3 x minus 1. Don't forget to add your 2 at the end. All right, I need to distribute. 3 times 1/3 equals 1x. 3 times negative 1 is negative 3, plus 2. This simplifies to x minus 1. No. Right? Doesn't work. It has to simplify to just plain x. So I can quit. All right, let's look at the next one. F of g of x. So for x, I'm replacing it with all of this, square root of x plus 5 squared minus 5. Now remember, the squared and the square root are inverses, so they cancel each other out, and I am left with x plus 5 in my parentheses minus 5. 5 minus 5 is 0, so this composition equals x. Now let's try the other one. G of f of x. Oh my goodness. X has to be replaced with x squared minus 5. And then keep your plus 5 from g of x. Clean this up first. Square root of x squared. 5 minus 5 is 0. And you know that the squared and the square root are inverse of each other and cancel out. So this simplifies to just x. So yes, these are inverses, and you have verified it. In order to verify, you have to show the compositions. You can't just say yes or no. Okay, think of verify like a geometry proof where you have to show every step. You can't skip anything.